that leaves the last quantity to consider, and that is the displacement. How much ground does the ball or the object cover as it rises and falls? Well, if you look closely, you can see that I kind of drew this with some purpose. If you'll notice the object here, right, you'll notice this distance, okay, is larger than this distance, and so on, okay, and actually the amount of ground covered gets smaller and smaller as you slow down, and then of course as you come down, right, it gets larger and larger. Just like in accelerated motion, like a car moving on the surface of the road. So we can actually, in both of these cases here, okay, with velocity and acceleration, we can actually use our equations that we learned to work these numbers out. Now I did these in my head, all right, we just sort of, because they're easy with the number 10, but you can actually use the equation too. In fact, let me show you. Right here, okay, at the beginning, let's try this. We can go velocity equals, okay, so if my initial, the ball left the thrower's hand with a speed of 40, right, it had an acceleration of -10, and it went for 1 second, right? How fast will it be going 1 second later? Well, we already worked it out in our head, it's 30. But look, the equation will give us the same answer, right? 40 plus -10, okay, v equals 30. How cool is that? Okay, so these equations still work, right? It's accelerated motion, it's just we're going up and down now instead of right and left or north and south or east and west. We're just going up and down, we're going to call it up positive. Okay, well the same thing goes for displacement. You can also use the displacement equation to figure out how far an object travels in that first second. So let's do the same thing. Let's figure out how much ground it covers here in the first second. Okay, I didn't start this problem as good as I could have. I should have been more clear about my coordinate system. I did tell you which way was positive, but I didn't mark where my origin was. So I'll do that now. We'll call this the origin, okay, down here where the ball leaves the thrower's hand. And so that makes the initial position of the ball, right? I mean, it starts at the origin, so that makes this 0 here. The initial velocity when the ball left the thrower's hand was 40. We want to know how much ground is covered 1 second later, so we'll put a time of 1 second in here. 1/2 -10, and then 1 squared. 1 squared like that, okay? And then we just do a little math here, work this all out. It's going to be 40 plus 1 times 1 is 1. -10 times 1/2 is -5. And you can see that in that first second, okay, the object covers 35 meters. 35 meters. So now we've figured out the displacement, right? The displacement of the object in 1 second, and we've also figured out its velocity after 1 second. We've used those same equations, okay, that you're already getting familiar with, but we've used them in a new context, the context of free fall. Okay, we're almost done. We're going to go to one more screen here. We're going to just kind of see, really the last thing we need to do is sort of get an idea of how displacement changes in time, and in order to do that, we're going to want to finish our graph here. Okay, I'm actually going to go, it's getting a little busy on this screen, so I'm going to go to the last screen here. Okay, and it's the same drawing reproduced, so we just need to fill in our graphs quick here that we already have. Okay, for example, velocity. Okay, and then down here we had this one already. Right, we already know acceleration to constant 9.8 the whole time. Got that, or -10 in this case. Okay, and we just got to work on this last one here. Okay, and we already figured out that from the previous screen, okay, that in the first second, the object moved 35 meters. Okay, and you can see from the drawing, like we've already discussed, and you already know that when an object's accelerating, it either covers more and more ground each second or less and less ground each second if it's decelerating, slowing down. So what we're going to do is we're going to use the free fall equation one more time, or not the free fall equation, the displacement equation one more time, just so you can get an idea here. What happens in the second, like right here? Okay, what happens right there? Well, let's try it. At this point here, okay, we know that the object is now at 35 meters. Okay, it started at 35, so if you want to start the problem from there, it started at 35, okay, and at this point, the ball was no longer traveling at 40, it was traveling at 30 meters a second. We want to see how much further it goes in the next second, so we're still going to put 1 there. Or you could say 2 minus 1, right? The second minus the first second, still 1. Plus 1/2, negative 10, 1, run out of space here, squared. Okay? And when we work all this out, we'll say it's going to be 35 plus 30 plus negative 5. Okay? And of course, that is going to be 60. All right? Now what that means is that actually means that this distance here is 60. Okay? It means that that distance is 60. It means that after 2 seconds, the ball will be 60 meters from our origin, which we had marked as down here. But if you do 60 minus 35, you'll see that in the second, right? In other words, right here, okay, it only covered 25 meters. Whereas in the first second, it had covered 35 meters. Okay, and so what you see is the math confirms what you already know, which is that when an object slows down, it covers less and less ground. And so what that's going to look like on the graph, okay, if you come back over the position time graph here, is we're moving in a positive direction, right? We're still moving up. So more and more positive, but we're slowing down. So it's going to be a curve, right? So I'm going to come over here. I'm going to slow down while moving away. At the very top, right here, I momentarily come to rest. Right, so it flattens out, and then I begin to speed up in the negative direction. Right, speed up in the negative direction. So that's going to be a steepening curve down. I wonder what shape that curve is. Oh yeah, parabola. Right, it's a parabola because look at the equation over here. Right, isn't this an equation in to the power of 2, and therefore it is a parabolic quadratic equation. Right. So there you have it. You have your motion graphs for free fall for an object that's thrown up and falls back down to where it started. You have the application of the acceleration due to gravity, right? Negative 9.8 or negative 10 meters per second squared, and how it affects an object in free fall. And you get to see that even though this seems like a new situation, free fall, objects rising and falling, the same equations still apply, right? The same free fall equations still apply. So I think that's a good start. We'll bring this information, this knowledge to class, do some more practice, and get you on the road to physics mastery.